Hello, Chem B. I just wanted to make a little video um, doing an example of empirical formulas, one that I didn't get to today, and just so you guys can reference it, or for anyone who wasn't there in class. So let's say this is Dr. Dana Scully of the FBI, a la X-Files. And she has identified that the percent makeup of some unknown compound here, by mass, has the percentages 12.1% carbon, 16.2% oxygen, 71.7% chlorine. Okay, and again, this is by mass, not by moles or by molecules or by atoms, but just by the mass. So don't worry about exactly what experimental procedures are necessary to get these numbers, but the point of something that's empirical, means found through evidence or observation. So this is different than what we've been doing through most of the class, both last term and this term, where things have been predicated mostly or entirely on theory. So you're basically given a hypothetical experimental set of data where these are the masses of some compound by the percentages of the masses by weight. So how can we do this? How can we figure out the so-called empirical formula? Well, the empirical formula is kind of like a molecular formula. But while it may capture the right ratios, it may not have the actual correct numbers of the molecular formula, which is fine. The empirical formula is still very powerful. So let me just give a little example here. So if I wanted to find the empirical formula of this unknown compound, I want to find the ratios of the numbers of the atoms themselves. Another way of saying this is I want to find the ratios of the moles of each of these. But the moles, remember, are going to be related if I use little n to be the number of moles of an element, and I use mu as usual to be the molar mass of an element, then I can say, let's say I have 100 grams of this substance. Okay, 100 grams total, which would mean 100 grams of the compound would be broken up into 12.1 grams of carbon, 16.2 grams of oxygen, and 71.7 grams of chlorine. 100 is just a convenient number to work with, but because we're only interested in the ratios, the actual number that I set it to doesn't really matter. You could choose 100 or 1,000 or 1. 100 is just convenient to convert for percentages. So now, how do I get anywhere with this? Well, I'm going to need the molar masses of each of these so that I can take the ratios of them. So let's start with carbon. So I'm going to call N sub C the molar mass, or sorry, the number of moles of carbon. And I can convert this from the amount that I have here, the 12.1 grams of carbon, using the molar mass of carbon. So I just take 12.1 grams, and I'm going to multiply now by 1 mole per whatever the molar mass of carbon is. So if I scroll down to my periodic table, and I look here and I say, oh, molar mass of carbon is about 12.011. Okay. All right, I'm just gonna say 12.01 grams. Okay. So this will give me the number of moles in this correct ratio here. So I'm actually going to end up with something very, very close to 1 because I'm going to have 12.1 divided by 12.01. Now the grams wonderfully will cancel and I'll be left with moles. Okay, so the number of moles of carbon in this hypothetical 100 gram compound is going to be about 1.01 moles carbon. Okay, and now I'm going to hold on to this number for later, for when I take my ratios. I need to do the same exact thing with oxygen and chlorine. So let's do it with the oxygen. So then my number of moles of oxygen, how do I find this? I'm going to go here and find, okay, 16.2 grams of oxygen. And I'm going to multiply that, grams of oxygen, by, once again, 1 over the molar mass so that the units work out. Need to go find the molar mass of oxygen. Okay, what is that? Oops. That is nearly 16, 15.99 or so. I'm only going to work to 2 decimal places, just to keep it simple. And so what do I end up here? By the way, this squiggly equal sign means approximately equal to. This turns out to be, once again, about 1.01 moles. But of course, this time it's moles of oxygen. So again, we had our grams cancel out and we were left with moles. So I'll hold on to that. And finally, for chlorine, go back up, there was 71.7 grams chlorine. And again, I will need to find my molar mass of the chlorine on the periodic table. It looks like it's 35.45 grams per mole. So 35.45 grams. And this turns out to be about 2.02 moles of chlorine. So these are my 3 numbers that I need to look at here. So I'm going to just copy them back down. So we have moles of carbon, 1.01, moles of oxygen, 1.01, moles of chlorine, 2.02. These look very, very close to the whole numbers 1, 1, and 2. Okay, so we allow for the possibility of there being some experimental error here, or even rounding error that could have led to things not being exactly integers. Okay, so I can look at this and say, hey, this looks a lot like a ratio in the form of 1 to 1 to 2. Specifically, this would be 1 carbon to 1 oxygen to 2 chlorines. Okay, so note that there's a matching here that you have to do to figure out which of these goes with which number in the ratio. You got to be careful. But if you are careful, you've done all the work and you have the empirical formula now. What would the empirical formula be? Well, it would be 1 carbon, 1 oxygen, and 2 chlorines, and we'd indicate the 2 chlorines with the little subscript, just like we do in water. And that would be your final answer. That right there is the empirical formula for something called phosphine, which is a deadly gas that was used in World War I. A fun fact.